Okay, continuing with our nonmetals, we're going to talk about the noble gases. And again, remember the noble gases are that group that they're kind of stuck up. And the reason why they're stuck up or they're unreactive and they don't like to hang out with anybody else is because they are full. They've got a full octet, except for helium, which only has two. But again, hydrogen and helium only need two because they're so small. But everybody else needs eight. They got eight. They're happy. Okay. So they have very high ionization energies because they have full valence electrons. They just don't want to, they don't react with anybody. Okay. Liquid helium, which has a boiling point of 4.2 K, so what would that be? 273 added on to that, so 277, 278 about, is used as a coolant. And it's found in a lot of natural gas wells, okay? Neon, argon, krypton, they're using lighting, sorry, not lighting. You've probably seen neon lights before. There's it used in displays. There's also lasers. They're really nice to use in lasers because they're so stable. You're not going to have an issue because of them. Okay. Argon is used in light bulbs. It's also used argon welding. It's very protective. Area, you use it as a gas to mix with the other ones to help protect you so you don't get like explosions. Again, noble gases are very, very, very stable. Okay. The noble gas compounds haven't been discovered that long, or the compounds, I should say. The noble gases were discovered. It took them longer to find the noble gases than most elements because they didn't react with anything, but they were discovered before 1962. But in 1962, they found out that there are a few of the noble gases, especially the guys down here, xenon and radon. Because they're bigger, they tend to form, whereas these guys up here, not so much, okay? But you can see xenon right here is the one that really forms most of the compounds. And it does change its oxidation, okay? They have different melting points. They have lower ionization energies, and so there they can expand their valence shell electrons. So they can add things. They can form, and you can see mostly with fluorine and oxygen, okay? They do, krypton, they say it forms a few, but it's really, really unstable. But if you take xenon and combine it with either fluorine or oxygen, you can get some compounds. So there are a few compounds that noble gases make. Okay. The halogens would be right over next to the noble gases, and these are the most reactive of all the nonmetals. Fluorine is by far the most reactive of all nonmetals. Okay. You can't replace fluorine in any reaction. It's the most reactive of all of them. But you can see fluorine, chlorine, bromine, iodine, and astatine. Okay. They are the salt formers. That's what halogen means, salt formers. They have very large negative electron affinities. In other words, they've got 7. They just need one more. So they're they have very, very large ionization energy. They just need one more electron, and then they'll to form their anions. Okay. Other than fluorine, they have higher oxidations. So they can get higher than +7, but fluorine's always -1. It's never anything but -1. The other guys can change, but not fluorine. Okay. Chlorine, bromine, iodine, they will exist as anions in brines. Like if you get seawater, you will find chlorine, bromine, and iodine in them. You can only find fluorine in minerals. Okay. They're very, very unstable. Okay. Again, they don't want to be just fluorine. They want to be combined with something. Okay. They have a very unstable radioactive element, and they don't really know much about it because it doesn't last very long. So, it's hard to study it if it doesn't last. Okay. The halogens, most properties vary a lot from fluorine to iodine. Okay. They are diatomic, which they all share that. When they're in pure form, there's always 2 of them. Weird things like you've got iodine, which is a solid, bromine, which is a liquid, and there's only 2 liquids in the elements at room temperature. And then you got chlorine and fluorine as gases, so you've got that variety. They're not in the same phase. Fluorine, like I said, is very reactive. It's hard to work with fluorine because, again, fluorine wants to combine, okay? The halogens are very good oxidizing reagents, okay? So, again, fluorine is the most reactive, iodine's the least. If you look at some of the things there, how their radius changes, chlorine's almost pretty much double the size of chlorine. So you've got a big change from fluorine to chlorine, and then it isn't as much. Okay. But again, fluorine is very, 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 very reactive because it only needs one, and it's the smallest of all of them. So It's hard to work with fluorine because, again, it's so reactive. Okay. If you're going to get halogens, you're going to get them from a salt. Sometimes they take an oxidation of a halide anion. Okay. That would be, it means you have something with oxygen. Okay. Halides are oxidized by electrolysis of salt solutions. So here's sodium fluoride, sodium bromide, sodium iodide. They added chlorine to them, but they get the other one. But the only one that really works well in that layer, you can get your bromine and your iodine, but it won't happen with the fluorine. Because again, remember fluorine, you can't break it. Chlorine can't replace fluorine. It can replace bromine, it can replace iodine, but it can't replace chlorine. So the only way you would get, if this was NaCl, you'd have to put fluorine up here and then it will replace all of them. Okay. Fluorine has an unusual high reduction potential, so it can easily oxidize in water, so they can get it from electrolysis, and they can get, it won't take as much energy like if it was hydrogen and oxygen. Okay, but fluorine is, in that sense, is unique. Okay, what do we use halogens for? Well, fluorine reacts to form fluorocarbons. So if you take carbon and fluorine, and fluorocarbons are used in lubricants, refrigerants, plastics. If you remember from chapter 18, though, we got to be careful with CFCs, chlorofluorohydrocarbons, because in refrigerants, they break down the ozone. Okay, Teflon, if you have Teflon pans. Now I think everybody has more stronger ones like Silverstone and all that, but Teflon was, oh, it was the bomb when it first came out. It was a polymer of fluorocarbons, so it's a very strong substance, okay? Chlorine is the most used of all the halogens. They use it in hydrochloric acid, which is a very strong industrial one. They use it in plastics. They use it in bleaches. It's a great disinfectant, chlorine. Any of you that go to the pool know what I'm talking about. They use it in water purification. They put a little bit of chlorine in our drinking water, not like a pool, because obviously they don't have to kill as much bacteria if you're going to drink it as opposed to swim in it. Okay, we have iodized salt. In your salt, they'll have potassium iodide that they add, and it helps your thyroid. If you don't have iodine in your system, you can get a goiter where your neck is huge. It's like swollen on both sides. And it's from your thyroid swelling because it doesn't have enough iodine. Okay. The halides, again, hydrogen halides, all halogens form stable binary compounds with hydrogen. So you have HCl, HBr, HI, so on, HF. Those are all acids. Hydrochloric acid, hydrobromic acid, hydroiodic acid, hydrofluoric acid. Okay, HF will form with silica to make like glass. Okay, so you can see some in there. Here's an example. SiO, this is sand. And then you add the hydrogen fluoride and you can end up with, this is a glass substance. So you can use it in etching in glass. Binary compounds, again, are made out of two different halogens. There's a couple of those. Sometimes, so you get iodide trifluoride, iodide pentafluoride, better say it right. Those aren't super common, but it can happen where you'll get one in the middle and then you'll get halogens around it. Iodine and chlorine are formed quite a few, and again, used a lot in medical applications. They're very powerful oxidizing agents, so you got to be, they're stored separate. I know in the lab we have 4 different compounds, or 4 different types of compounds. 3 can be stored near each other and 1 can't. The oxidizing agents have to be stored in a different place. Okay. And we have oxyl acids and, I'm looking at time, oxyanions. Okay. Oxyl acids, their strength increases with increasing oxidation number. Okay, oxyl acids would be like sulfuric acid, phosphoric acid. Down here we have hypochlorous acid, or chlorous acid, and then we have chloric acid, and then we have perchloric acid. And they're just using the end part, and then you put the name in here. So this would be hypobromic, or bromous acid, sorry. They don't even have this one. Then this would be bromic acid, and this would be perbromic acid. So they have ways, and again, chlorine here, bromine here, iodine here. That doesn't happen with any other thing but the halogens and oxygen. Okay, oxyl acids are very strong oxidizers. That makes sense. Oxyl anions, so that would be where you get negative, are generally more stable than the acids that they break down into. And perchlorates are stable unless heated. So they can use perchlorates in rocket fuel. Okay, so again, this is when you're adding oxygen to, again, I know it's an acid because I have hydrogen listed first, and then I have a halogen, and then I change the oxygen. Okay. Oxygen, we know, is the most abundant element by mass. Okay, there's more hydrogen atoms, but hydrogen don't weigh very much. Oxygen doesn't weigh a lot either, but it weighs a lot more than hydrogen. So in the Earth's crust, in the human body, by mass, there's more oxygen than anything else. Okay, we have two allotropes, two forms of oxygen. We have oxygen gas, which is O2, which you hear about, and then we have ozone, which is O3. Okay, ozone is less stable. O2 is the way oxygen really wants to be. That's the most stable form. Okay, the properties of oxygen gas, we know it's colorless, it's odorless, it's only slightly soluble in water. The colder the water is, the more it dissolves, because again, it slows it down. But it's a small molecule, so but without it, yes, marine life, all things in the water would die. So it's important to have it in the water. Oxygen likes to bond, like elemental oxygen forms diatomic. It's a strong double bond. So between two oxygen, in order to get it stable, so both have 6, you have to form a double bond. The bond enthalpy, that's how much energy it takes to break the bond. So it's a pretty strong bond. Okay, it's covalent. It shares its electrons. If it's ozone, it'd be single bonds. If it's O2, it's double bonds. And they're very strong. Again, they're much more stable than the element by itself. That's why it combines. Okay. Oxygen will form an ionic compound with just about any metal, okay? Because it's looking for 2 electrons, so it needs to fill that. So that's why its oxidation number is -2. It has 6, it's looking for 2 more, okay? Looking for 2 electrons, okay? To get oxygen, nearly all the oxygen is obtained from the air. I always like when they have the shows where you have your little oxygen tank and it makes oxygen from the air. No, what it does is it extracts oxygen from the air. It concentrates it. They're called concentrators, and basically what they do is they keep the oxygen and kick everything else out. Okay? Oxygen gas boils at a higher temperature than liquid nitrogen. So if you take air and you liquefy it, you cool it down, okay? Liquefied air is warm it'll cause the nitrogen to boil, and then what's left over is going to be your oxygen, okay? So in the atmosphere, oxygen is replenished by photosynthesis. What would we do without our green plants? They produce, if you look, if this is your 2 products, this is respiration. If it's your 2 reactants, it's photosynthesis. And the 2 of them are supposed to work together. Unfortunately, we've kind of messed that up a little. But the nice thing about plants is they take in carbon dioxide and water, which we give off, and they make us glucose and oxygen. So a lot of the oxygen we get in the air comes from plants. Okay. What do we use oxygen for? Oh, we use it for all kinds of things. We use it, again, it's used as an oxidizing agent. So they use it in steel to remove impurities. Steel, you guys, is not an element. Steel is made up of, it's an alloy of iron and chromium and carbon. There's stuff mixed in there. Okay, but it gets rid of the impurities so it lasts longer. Bleach pulp and paper. Okay, welding, acetylene, they use it all the oxygen all the time in welding. I think up here is your standard combustion reaction. Okay, look at the energy release. This C2H2, that's acetylene. Plus oxygen, you get carbon dioxide and water and a lot of energy. Okay, and then we talk about ozone. Ozone is a pale kind of blue. If you've ever plugged in something and it kind of zapped, you kind of, and then you smell it, the kind of a weird bitter smell, real sharp, that's ozone. Ozone is not good on Earth. Ozone can be a pollutant. It can cause lung damage, okay? It's really, really irritating to the respiratory system when it's on the ground. So it's a ground level pollutant. It's a very, very, very strong oxidizer. They use it like I have a hot tub, and it actually has an ozone pump. So instead of having to use a ton of chlorine, it uses ozone. And I think they're kind of moving more toward that because chlorine smells. I mean, it's a great disinfectant, but it smells and it can be kind of icky. So they're moving more toward ozone is using as a purifier. It works really well. In water plants, they use ozone as well. Okay, it's used in organic synthesis, so it severs those carbon double bonds. It absorbs UV light in the upper atmosphere. So ozone way up high in the stratosphere is wonderful. Okay, it